Hey guys, today we're going to be talking about forces, and we're going to discuss all the different types of forces so that way we can get started on drawing our free body diagrams for this unit. So first of all, we have to identify what a force is. In elementary school and middle school, you learn that force is either a push or a pull. That is fine, but it seems a little vague, so we have to understand the cause and effect of a force. And in this case, a force always acts on an object. So you know a force is present if there is an object. Anytime there is contact between objects, you're going to have a force. So here we have a person and a punching bag. We could consider the punching bag as an object, and I would describe the forces on that punching bag. Or I could consider this shot put the object, and I could consider the force the girl is applying to the shot put. Additionally, every force has an agent. So what causes the force, what's behind the force, what's doing the pushing or pulling, that's your agent. So in this case, this guy is the agent punching the bag, which is the object, and here we have the football player, which is the agent, applying a force to the football, which is the object. So agent-object is going to be pretty simple to figure out. We call them feeler-dealers. The object is what's feeling the force, and the agent is what is dealing the force. So later on, we'll be looking at agent-object notation or dealer-feeler notation. So next we need to understand that force is a vector. Now if you remember, we have described many different quantities with vectors. A vector is an arrow, and that arrow has direction and magnitude attached to it, meaning the longer the arrow, the stronger the force. Or when we looked at velocity, we said the longer the arrow, the faster the object is moving. And also the end of the arrow here represents the location of that force. So in this case, if I was interested in drawing forces on the ball as the object, there would be a force in this direction. Depending on how hard the pull stick is hitting the ball, that would determine how long I draw the arrow. So just like velocity and acceleration, we'll be drawing arrows for forces. So there are two types of forces you need to know about, or two broad categories, and those are long-range forces and contact forces. So first of all, long-range forces are forces that can change based on location. Examples of these are the force of gravity and the electric force. And those are the two main forces that we're going to discuss, or really gravity is the only one that we will discuss that you're going to need to really understand as a long-range force. Every other force is considered a contact force. And it should make sense what a contact force is. If you have objects that touch or come into contact with one another, then you have a contact force. So here we have an example of a bat hitting a ball, or in turn, later on we're going to learn Newton's third law, we could say the ball is also hitting the bat. So in discussing contact forces, I have a question for you. We should be able to first identify what type of force every force is, whether it's long range or contact. So let's just think of air resistance or drag. You may not know much about drag, but what you do know, you should be able to figure out, would that be considered a long range force or a contact force? Okay, air resistance is actually a contact force because it's due to those air particles that are coming into contact with the object. Okay, let's talk about weight. Weight is also the force of gravity. You're going to hear me use those interchangeably throughout the semester. Weight can be written with a capital W, or it's most commonly notated as the force, or the F standing for force, and then a subscript of G for gravity. Now, one thing you need to know about weight is that it always points straight down. Every weight vector that we draw will always be straight down. Whether you're on an incline, whether you are standing still or running, it doesn't matter. An object's weight always points straight down. And that's because if you're on Earth, or any planet, and you drop an object, no matter where you're at, gravity's going to pull it straight down towards the center of the Earth. Now, really, the direction is towards the center of the Earth, but if we are talking about objects on Earth, then that surface we have to assume is flat because it's so huge compared to our object. So, if I were going to draw the weight vector for this person on this incline, it's going to go straight down. Again, it does not matter whether the person's on the incline or on a flat object or just falling through the air. Weight always points straight down. Okay, the next force, we won't see this very often, but anytime there is a spring that is stretched or compressed, then you have the spring force. And that is when the spring acts as the agent and the spring actually pushes or pulls on something. In this case, when the spring or when this box is stretched, the spring is trying to pull it back to equilibrium. And in this case, when the spring is compressed, the spring is trying to push it back to equilibrium. The next force is tension. Tension is present when there are ropes and fabrics and chains, any object that can be stretched or pulled tight. Tension will always go along the rope. So in this case, we have two tension forces, even though there's only one rope. We would say there's a tension force here being caused by this group of students and a tension force here being caused by this student. Now these two tensions are going to be equal because regardless of where you're at pulling on a rope, the tension is always the same in that rope. No matter how hard someone's pulling over here, that's going to equal the amount that this person is pulling. And that deals with Newton's third law, which we'll look at a little later. Now here we have a sign. And if I were to draw the forces on this sign, I would say there's a tension force there and a tension force there, because this string actually comes into contact with the object, the sign, in two different locations. So notice my tension force always starts at the object and is going to go along the rope. Next we have the normal force. The normal force is one of the more difficult ones to understand, but if you just follow one simple rule, you'll never get it wrong. The normal force is always perpendicular to the surface. If you remember in math, normal is actually the term used for perpendicular. So when you have two lines that are normal to each other, they're perpendicular, meaning it's going to make a 90-degree angle with your surface. The normal force always comes from a surface supporting an object. The surface could be the ground, it could be a table, it could be a wall. If I were to push back on this wall, then the wall is going to apply a normal force back on me. So in this case, this vector represents my normal force, whereas this downward vector would represent the weight of the object. Here I have an incline with the normal force shown. Again, it's 90 degrees. If I were to have a different incline, then I would have a different normal force, but it's always perpendicular to your surface. Okay, the next force we have is friction. One thing about friction is that it always opposes the direction of motion. So if you are moving to the right, friction is going to go to the left if it's present. Friction is that force that always slows objects down. So in this case, let's say our object is this baseball sliding into base. Because the baseball player is moving to the left or sliding to the left, friction is going to be trying to slow that baseball player down or pointing to the right. And here we have two examples. Your friction is going to be different depending on the type of surface that you have. If you have a surface like ice or a very smooth or oily surface, then you're going to have little to no friction, so we can represent that with a very tiny arrow for friction. However, if you're on grass trying to slide, it's going to be very difficult, so we're going to have a larger frictional force. And you can see that the frictional force, even though my heel is inclined here, My frictional force is always going to be parallel to your surface. It's always going to be the same direction as your surface. If you're on a hill, then your friction will be slanted. If you're on a flat surface, then your friction will also be flat. Next we have the drag force, or this is also called air resistance or air friction. Just like regular friction, it opposes motion. So here we have a skydiver who is parachuting down, and lots of air is hitting up under this parachute, but we can say all of that air is concentrated at one point and pushing against the person in that direction. Remember, it's opposite of motion. Same thing with a leaf. We have a leaf falling, so it's going to have a pretty small amount of air resistance, but it is present. The thrust force is present when any gases are used to cause an object to go forward. So in this case, you'll see thrust when we're talking about planes and anything with like big engines or a rocket thruster. So here we have an example. Here's a rocket. Notice it goes in the direction of motion this time. Unlike friction, thrust goes in the direction of motion because we say these gases are pushing that object or the rocket this way. And if we're talking about a plane, the thrusters would go in the direction of motion. Those engines are pushing that plane forward. We have the electric and magnetic force. Now we won't see this very often, but anytime you have a magnet, then you're going to have the magnetic force. And that's always an attracting force. So we can say this magnet is pulling up on this object, and we can even say that it's pulling up at two separate points. Now the electric force could be attractive or repulsive, and we won't talk about this very much, but just understand that it is a force that exists. And finally, we have what we're going to call just a general force. If you have a force and it's not one of those specific types, it's not weight or friction or spring force or anything like that, then you just remember every force is either a push or a pull. So if I had a box that was coming into contact with another box and pushing it in a direction, then I would just say force push. All right, well, that's all of our forces, guys. Your job is to make sure you know when these forces are applicable, because we're going to start drawing free body diagrams, which means we're going to be identifying all of the forces acting on a single object in a certain situation. And as long as you can understand these definitions or have this catalog of forces, then you'll be good. Thanks for watching, guys. I'll see you in class.